Hi everyone, it's Judy Warner. Welcome back to the OnTrack podcast. We're glad you could join us. Today we meet with Rob Cooke and Jose Cordero from Calumet Electronics in Michigan. We talk about something that's often overlooked, which is making sure your data package references the most current revision of IPC standards. We talk about slash seats, we talk about ENIG, we talk about via plugging. I think you're going to enjoy the wisdom they have to share, so lean in and enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, Jose, Rob, thank you so much for joining us from beautiful Calumet, Michigan, where I just had a great joy to visit. So it's nice to see you both, and thank you so much for joining us today on the podcast.
Thank you for having us.
Well, let's jump right in. Jose, let's start with you. Tell us a little bit about your professional background and we'll jump into Calumet after, but just tell us a little bit about your own personal professional background.
Well, one of the many things that we share in the industry is that you don't go to college to end up in PCB fabrication. So my background is actually in arts and sound design specifically. I was born and raised in Puerto Rico. I left the Caribbean to come to the north side of Michigan in the UP to go to Michigan Technological University, where I got my degree. And after I graduated, I found Calumet Electronics, and I just started there like any other temporary job that you start as a right out of college type job, and eventually I've grown into the industry and enjoyed it and decided to stick around.
It's funny how much, so I was raised by an artist as well, and it's very funny to me how much sort of art and science cross paths and really capture our imaginations. I never thought I'd be in the printed circuit board industry. So, Rob, how about you? Tell us a little bit about your background.
Sure. I've been in industry for about 18 years. I spent a majority of my career doing design work in electronics for aircraft and military systems. I've done a lot of low-level board design, as well as layout and routing and the whole works, and moved into project management, and now I'm working as the Director of Engineering at Calumet, which is a pretty recent move for me. I started about 3 months ago.
Wow. So do you appreciate manufacturing more than you did before, or were you pretty well versed in it before you joined Calumet?
Absolutely. I think designers really have a good understanding on what they want the end board to do, but they quickly get lost in some of the details of what it takes to actually get there. And so that's one of the things that's been a lot of fun to get engrossed in and get hands dirty on, is the specific processes that get you those blind and buried vias, or the tight controlled impedance traces that you need for signal integrity.
I bet you don't see boards as just a random item on a BOM anymore.
Yeah, I never did, though. I mean, when you're an electrical designer, you understand how important the board is to the overall design. But I do see that as something that people can quickly overlook. It's not just one more part, right? It's an integral part of the design.
Yeah, it sure is. Well, Jose, since you've been with Calumet for some time, Calumet, when I came to see your folks, you told me it's 50 years old, which is a long time. So could you give us a little bit, or maybe you both want to jump in and give us a little bit of the background of Calumet?
So Calumet, back in the day, was one of the largest suppliers of copper, both for the nation and the world. And then, as the mining industry started to reach the end of its life, the people in the community that wanted to preserve jobs for the area and wanted to maintain the boom of businesses and everything continued to grow, they decided, well, what else can we do? And they made the leap from copper to, hey, these are used for traces and circuit boards, and they started the company with that in mind, and the thriving the community by having something to replace the jobs that were lost when the mines closed down.
That's really great. So I should mention here for our listeners that Calumet is a city, and Calumet Electronics is a factory. So they bear the name of the town. So just so you don't get confused there, is that Calumet was a big copper producer. And so what a neat story. And I'm going to share with you guys sent me a link that I'm going to definitely embed in the show notes. It's a video sort of with pictures of beautiful Calumet with these beautiful architectures and some of the old copper mines, and I think it's a really neat story. So thanks for sharing that.
Yeah, we started as a small shop in a building that was acquired by the general store owner in town. Moved into a church. After that, moved into an old railway roundhouse, which is where our factory currently is, and we've expanded ever since to the point that today we're producing somewhere between 600 and 800 panels a day and produce over 3.5 million parts per year.
That's just amazing. That's a lot of boards and a lot of panels. By the way, going through Calumet, the factory, just a couple weeks ago was amazing because we were going through your imaging area and whatnot, and I'm like, why are we walking in a circle? Because it is a railway roundhouse for real, and it's a really unique architecture for a circuit board facility. Has a lot of character.
Definitely adds a little bit of a challenge and ingenuity in how to lay out the production floor when it goes around in a circle. But
yeah. So, well, what I thought we'd talk about today, guys. So, Jose, you're running the front end on CAM, and Rob, you're handling a lot of the engineering functions. So, what I want to talk to you about is when designers design boards, they send you over a data package. What are some of the things that sort of slow down getting that board put through your shop?
One of the things that, funny enough, just happened a little bit before we started our podcast here, is the IPC Material Callouts. There is a lot of confusion still in the industry of what these callouts mean, what they entail, and then the materials that are associated with them. Back in 2017, there was a major update to IPC 4101 that changed the nomination of what materials are grouped under which category. And we still see materials being called out with the old spec with the intent of using what the new materials are. And it's hard both from our perspective when the customer is expecting material certifications that call out a certain slash number, and we're technically providing what they're calling out, but we can't put the number that they're calling out because it no longer meets that material certification. And trying to sometimes we're communicating with an assembly house that not necessarily may know the intended design requirements. So then they have to go to their end customer and confirm whether that's the material that they need.
Sounds like a bad game of telephone.
Yes.
And what we really need is to have a good handle on our designers looking through their fabrication notes. I know in a lot of cases the idea is to just reuse the same material callouts as we did on the design from before and the design from before, and you quickly miss that update to that IPC 4101 spec. And especially when it's a part that's a medical or an aerospace or a military part where the design was produced 5 to 10 years ago, but the specs change over time and the material availability changes over time. And so there's got to be some diligence and willing to discuss with us how to get it up to speed. And make it so that we can provide you what you need from a design intent. We're pretty good at being able to help make that transition in materials because we've been living with it every day. And so that's what we want to be able to do with our customers, is have those conversations.
Yeah, of course. Well, Rob, to your point, what do you think has sort of led to this disconnect? Why aren't designers sort of up to speed on knowing this update happened in 2017 on this specific instance?
I think what it boils down to is the pace of change can really accelerate the development of the spec, and that the designers are looking at materials that are low loss, are different dielectric, and really trying to see what can be done as state of the art. And then they are not always able to keep up with that material in the spec. And when IPC does make those changes, they're not always well communicated out to the end users. They may not be looking through IPC standards every day to check for an update. And in this particular case, it was a fairly significant change rollout that a lot of folks in industry who weren't very close to the IPC didn't realize was happening.
And we actually found out through our material suppliers who, kind of gave us a heads up. It's like, hey, these changes are coming. These are what our materials' new classifications are going to be. These are the equivalents if you want to make substitutions, so that you're aware. And we used a lot of that documentation that was provided by our suppliers to then pass it on to our customers.
Great. What's kind of ironic about this, you guys, is that John Mitchell, who's the CEO of IPC, has been on the OnTrack podcast before. And I remember one thing that he said that IPC was trying to address is that the industry was complaining that they were taking too much time to roll out new standards. So they've intentionally, shortened that time down, right? And so part of me is wondering if it got changed faster than I think a lot of designers may have anticipated.
And that can be applied to just about everything. Both Rob and I were down to the IPC Expo earlier this year, and one of the concerns was that IPC could not keep up with the change of the industry. But then at the flip side, then sometimes changes come too fast, and then the industry can't keep up with updating everything that needs to be updated.
Well, that's why you're on the OnTrack podcast, so we can get the word out, right, guys? So, well, that's really interesting. So you mentioned, was it 4102? That was regarding the slash sheet. So
4101.
4101. So I think you mentioned to me something about via types. Could you talk to me about that, either one of you, whoever wants to field that question?
Sure. There are 7 primary via types described. The IPC spec is 4761. Mm-hmm. And sometimes there's some of the main ones are used interchangeably, even when that's not necessarily the intent. The two main ones are type 5 and type 7. Some of the other types are used to describe some legacy via structures.
Mm-hmm.
But the type 5 explains or describes vias that are filled with the LPI ink to plug the hole. And type 7 is when you use a conductive or non-conductive epoxy, and then you cap and plate it over, which is usually the intent if you want to have a via at the same location that you're mounting your device to. Each one has its own set of processes associated with them, and picking the right one can make a difference between both your turn time and your total board cost. Of course, the planarization, which is the type 7, has additional plating cycles, additional materials to fill in, whereas with the via plug, you're already using your solder mask, so you don't have to add additional materials to your BOM. And also, when you're adding all these additional plating cycles, you also have to then do the actual planarization, which can cause unevenness on the total copper thickness, and that can present some challenges during etching as well.
I see.
I think what we see is that a lot of folks are trying to specify some level of filled or capped via, and they're applying, they're not using a spec, they're not using the IPC spec, they're coming up with some kind of design note on their own that attempts to explain what is covered by the IPC spec. And I think there's a couple of things that we see that really throw us off. The first is that they end up putting a cap, a planarized cap on every single via on the board, which is not needed. It's really usually only the via that's in a pad where you really need that more planar surface, or you're trying to get that covered appropriately. And then the second is they specify materials instead of a class of materials. And there's a lot of different epoxies and solder masks that can be used to fill those holes. If they call out the spec for the type 5 or the type 7, that gives us the freedom to pick and choose which materials are available from the cheapest or that are most conducive with our processes, and we still meet the intention of the via fill, but are not restricted by some note that calls out one specific type of epoxy that may have a 20-week lead time, or may be obsolete because Tayo or somebody else decided they weren't producing that anymore, or it got all allocated to overseas and none in the U.S. And really,
so are you plugging these? Oh, that was a bad pun right there. No pun intended, plugging. But are you kind of bridging this gap between you and designers by just having phone conversations, or what's the course of remediation for these sort of disconnects that are happening? Boy, I'm full of bad puns today. Sorry, you guys. It's not on purpose.
That's what happens when you live in the circuit board world.
Right.
One of the things that we've tried to alleviate the issue is anytime there's a discrepancy, or we're trying to question the intent of what they're specifically asking, we will actually send them a pre-written summary that we have. That way, we're always sending out the same verbiage, where we include some screenshots from the spec, and we explain the different processes. And then we give them the option to pick and say, hey, we want to go this way or the other way. Or if we think that they're trying to pick, for example, planarization, but by looking at the design, they don't have any vias in pad, they're all just covered by mask, then we will explain both of them, but then suggest the better alternative for their design. In the end, we still leave it up to them to decide one on the other, especially anytime that we're making any type of aerospace or military work. We definitely don't want to have to go through the reevaluation process of redlining prints and everything else. But whenever we have the opportunity to try to make the best choice for our customers, we try to do that for them.
So 2 questions. So does that typically result in them cleaning up their documentation and then getting the proper IPC standard or the type, via type spec'd in?
We've had some success there.
You don't sound that confident, Rob. Sometimes yes, sometimes no?
Well, a lot of it boils down to the challenges of revision control on a design that's for a military, aerospace, or medical application. We typically get a pretty good response to make those adjustments on new designs going forward, but the existing part that is trying to be built now has usually been through some level of certification, and so making an update or a change is not easy to do for that product.
I see.
And it depends too if our customer is a contract manufacturer or the original designer. Usually if we're dealing directly with the designer, we can get blanket waivers for their designs that, this note actually means this for them. We can enter into their profile and, we know moving forward, we build that relationship. But for most contract manufacturers or assembly houses, they can't say that it's going to be the same for all of their customers. So then we have to work more of a case-by-case basis.
I see. In your experience, I'm sorry, go ahead, Rob.
And that's why we're trying to encourage defining the plugged or capped vias by the spec, because it's the note that leaves room for interpretation or is ambiguous that causes the most problems.
The other thing I wanted to ask you about is whether you're dealing with contract manufacturers or the designers themselves, is it your sense that they actually have bought and have access to the IPC standards on these vias?
I would guess that someone in their organization does, but it's usually not prevalently spread through. Most larger OEMs have electrical engineers doing the designs, and then have a PCB layout engineer that's doing the board layout. The board layout folks will sometimes have access to those specs, but sometimes it's just their quality people that have access to the spec and not the actual engineer who's making the design decisions at the top end. It really depends on the size of the organization, the experience level of the organization. When you're talking about very critical boards in the power industry or in medical, they usually have someone in their organization with access to the spec. When they're more commercial or higher volume components or real specialty application, not as much.
Okay. It's interesting to see where these disconnects come in, right? So you're sharing the spec with them, but I'm like, I'm wondering, where that disconnect, is taking place. So it's interesting.
And to add a little bit to Rob's comment earlier about the vagueness of the instructions when they're not using the spec, sometimes they try to over-explain, and it gets so wordy that you have no idea which way they're actually trying to go. We had an order with 800 panels out in production that they had a paragraph of how they wanted their vias processed, And after we're halfway through production, they're like, "Oh no, change it to this other method."
Oh my.
And we were doing all hands on deck scramble so that we could meet the dock date while changing the process on the fly.
Oh my, that sounds terrible. But at least you caught it at a point in the process where you could scramble.
Yep.
So another area that you two have mentioned to me is about ENIG. So can either one of you kick off that conversation about things that have changed in the last couple of years in regard to thickness of gold?
I don't have the actual date for the change, but I know that it was a change that happened this year. Back in the day, there was an artifact of ENIG that used to be called the black pad, and while that doesn't get mentioned or seen as often now, since the specs have been moving in a way to try to minimize it, there's still a lot of issues with hypercorrosion, and it's been identified that more gold is not necessarily better. So one of the introductions and changes to the ENIG spec, which is 4552, is actually introducing an upper limit, whereas before there was only a minimum gold requirement. They're introducing now an upper limit to try to prevent that hypercorrosion that causes brittle joints and bad connections with those surface mounts. Which, again, it's another point of communication with our customers where they're used to there being a minimum, so they would either call out, 4552, but then also say 2 to 5 inches or micro inches of gold, or 3 to 8 micro inches of gold. And with the new upper limit, which the new range is actually 1.58 micro inches to 3.94. The signs that call out that 3 to 8, for example, is very hard to guarantee, since we would have a less than 1 micro inch of tolerance to try to keep it. If we
What? You can't do that, Jose? What's wrong with you?
Well, the main issue is not that we can't hit that tolerance. The main issue is that we target the middle of the range, and the middle of the range for our optimal level is around 2.5, and that's below the 3 minimum that is the call out on so many of legacy drawings. And to change the process to move it to 3 requires longer dwell times, requires changing the bath temperatures or other things like that to build up that longer, thicker plating. And not only does that slow us down from a factory perspective, it's also not really meeting the intention of the current spec and standard.
Right. So could you
people.
Okay. So could you take a moment and talk a little bit about what hypercorrosion is and why it's problematic?
This is an area where I'm definitely talking a little bit outside of my area of expertise, but I've done some reading to prepare for this. But the way that the gold is deposited on the nickel, it's through a replacement process where each atom of gold replaces an atom of nickel. So then the more gold that it's added, the more nickel it's removed. And when that removal process happens, it starts to create phosphorus molecules. And that the more of that phosphorus that gets built up there, the weaker the connections, and phosphorus is not a solderable surface, which then makes that joint weaker for mounting the components.
So
you're getting these. Oh, go ahead, Rob. Sorry.
I was going to say, I believe we started getting identification of this issue from folks in the medical community that were seeing or experiencing parts of this on some of the medical devices that they were soldering to. And so that's where that kind of push came into our knowledge sphere. And we then were getting passed down on us specifications requiring it staying below that threshold, and they have different classifications of what that hypercorrosion can be based on the total thickness of that gold on top of the nickel. And so we backed off in our process that way, and then the spec came out, and we made the wholesale change to adhere to the spec, and that's when we started seeing some challenges with legacy customer drawings that were calling out ranges outside of the spec.
I see.
And we actually we're trying to build closer relationships with customers that we can talk directly with engineers and bring them to our facility and show them our processes, and then we can mention some of these. Hey, why do you add these notes to your fab drawing? One of them specifically with in regards to ENIG, they call out latest revision of 4552, but then they also have the range, and their intent was to be informational. It's like, hey, in case you don't have the spec, or so you don't have to look it up, here's what the range is. But then same with the materials issue, then you have to be constantly updating if you're going to then technically try to quote the spec right after mentioning it.
So what I'm really hearing from you both, this is a very fascinating conversation, and something I wasn't aware of, is that designers really need to verify on their drawings, that IPC specs haven't changed.
Yeah, I think John at IPC would probably love the plug for that, but yeah.
Well, I think to your point, most companies, not all, I think have access to, that our members have access to the standards, but if not, I'm sure their partners would be happy to share them with you. But it's just an interesting thing that there's this disconnect between things that have changed and the way we're calling things out. And to your point, like, technology moves quickly, and then you've got these legacy drawings of products that have been building for years, right? And so it's an interesting thing. So you designers out there, check your IPC specs. The last
thing,
thing
to change when you made something that works, you don't want to break it.
True. True.
But when you're in a world where technology and materials are going at leaps and bounds with some of the capabilities, you have to stay on top of it. Supply chains are the biggest driver of that. All of the material and chemical suppliers are looking for newer, better, faster, and they want to push that down into the fabricators. So it's the materials that we're getting to start with that are really driving us, and that consistency that we can get from the spec just helps remove a lot of the question or ambiguity between how we interpret something and how the designer interprets it. At the end of the day, Gerber files, drill files, drawing notes, and fabrication drawings are a communication tool between the designer and the person who's trying to build it. And the more we can do to help ease that communication, the faster things flow and the more consistent we are with the build.
And another point to add on to what you just said, Rob, is depending on the industry, it's also a reference document upon which things are inspected.
Right. Yeah,
so
exactly.
That can be a problem too on the back end, and quality inspectors can give you guys as manufacturer a lot of grief for redlining or not complying exactly, because they're just using it as a comparison tool. So there's that.
We're probably our own worst enemy with that because our quality team is very diligent about making sure that they understand the letter of the law, and they have the ability and expertise to interpret these specs and standards and look at the notes in the fabrication drawing, and if we're not complying to them to the letter, they're likely to reject a part.
Exactly. And again, slows things down.
Worse.
Mm-hmm.
Yep.
So it's a very good point. Well, at this point, we're getting near the end of our time here, but we had hoped to maybe talk about panelization. So I'm going to throw it out to you. Should we do another podcast and dig into some of the issues that come up around panelization, or do you guys have? Will it, or can we throw it in here real quick?
We can definitely cover an entire podcast when it comes to panelization, but
all right.
We can definitely,
well, let's do it.
Have a quick recommendation to anticipate for that part 2.
Okay, all right.
Work with your, if you're a designer or an assembly house, work with your board house as early in the stages as possible. It's for the board house, the layout of the array or the pallet, whichever way that you want to call it. It's not as critical as it is for the assembly line. So for any assemblers out there, if you know your specs, you know your assembly line, the board house will gladly attempt to build whichever layout you desire that works best with your line. Otherwise, you end up a lot of back and forth. Hey, does this design work? No, we'll try a different one. Does this design work? Have that line of communication open, and make sure that any requirements or constraints about that assembly line get passed on to minimize the back and forth in that approval process.
And you're right, it is a lot more critical at assembly. So we want to maximize panel at manufacturing, right, for pricing and a variety of things. But once you start doing mechanical stresses at assembly, when you're, doing pick and place machines or whatever, and then there's the issues if you have, say, side-mounted connectors, the way you break them out, that can just create a whole disaster. So anyways, Jose and Rob, I'm going to take you up on part 2. So we'll just consider that a carrot dangled for part 2. So thank you both so much. This has been fascinating, something I really didn't know about. And so thank you so much for shining a light on it.
Well, we really appreciate the opportunity to let Calumet Electronics participate. We're trying to be relevant in our industry, right? We feel that what we do is an important part of the process for realizing all of the neat things that we use in electronics. And so the more we can help be a solution provider to contract assemblers, to OEMs and designers, we want to be those experts, and we appreciate getting the chance to share a little bit about what we know.
Well, thank you. And again, that is such a lovely attitude to have, because a good manufacturing partner will have that attitude. So, and won't see that as so much of a hassle to have additional conversations. So I appreciate your proactive attitude and willingness to be a good partner. So thank you both, Jose and Rob.
Thank you very much.
So that's it for today's podcast with Jose Cordero and Rob Cooke from Calumet Electronics. We hope you've enjoyed today's podcast. We look forward to being with you next time. Until then, remember to like, subscribe, and comment, and tell us what else you want to learn about. We're always happy to respond and get good guests on here to help you design well every day. So thank you for joining. We'll see you next time. Until then, remember to always stay on track.